All right. Okay, are we live? Hello, 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 hello. So, I think we're here. Howdy doody. Howdy doody. Welcome. So, good morning. I always have kind of a hard time like getting into things in the morning, so forgive me. But I wanted to take a look at the problem that I was working on yesterday, and it's a pretty interesting problem. I really messed up yesterday. I deleted the video because I fell asleep while I was thinking about it, working on it, and I'll give you one moment here. Is it this one? I think it's this one. Yeah. So yeah, basically I messed up yesterday. I got the wrong answer. Like I thought I memoized appropriately, but I was actually wrong. This memoization is wrong. So the way to solve this problem, I thought about it, and I was like, oh, I know what to do. I realized what I was doing wrong. This was 300. Really interesting problem. Pretty kind of hard problem. Of longest increasing subsequence. Yeah, really interesting problem. Challenging, new to me. Caught me off guard. I didn't really get it. Yeah, kind of somewhat beyond my experience at this point, but not beyond my abilities though. So here you go. Here's what you do. So you got this subsequence, right? Take this one, and what you want to say is, the dynamic programming aspect, or one way of doing it, is you can actually make an array. So it says 1, 2, 3, 4, 5, 6, 7, 8. So we want 8 by 8, right? 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, right? And what you would do, we'll use letters. So what you're going to do is you're going to loop from left to right over every number. So you have an index I, we'll put up here, and then you have an amount, we'll call it size, or size. And then what's going to be here, this number, so it's a three-dimensional function, right? So there's inputs up here, one dimension, the other dimension inputs there, and then what you have here is what basically what your function is going to store, what the value is going to be. So I'll explain. So at index 0, right? So there's 0, 0, 1, 2, 3, 4, 5, 6, 7, right? Oh, did I not make it? Wait, did I mess up? Oh, I needed one more. Whoops. That's my mistake. Yeah, I forgot I need one for this row. So I actually needed 9, not 8. That's my mistake. I need to increase these a little bit. Need to do the same over here as well. Just a little bit more. Huh. Okay. And the size is also going to be 0, 1, and I'll explain what this means, what this is supposed to be in just a moment. 7. Okay. Now, the idea is this. Why do I have this chart? So the idea is when you look at a subsequence, what you can keep track of is exactly what you could keep track of is exactly what you want to know is for any subsequence. So the maximum length of the subsequence is 7, right? That's the first thing. Like if any subsequence that you could have that's increasing, you can't have more than 7 because there's only 7 elements in the array. So you can't do better than that. So that's as far as we need to go in terms of the size. And then similarly, we only need to go this far. Also the same distance, again, because that's the only number of elements that even you can consider, right? So we have a sort of a fixed size for the dimensions here, and that's important. And then also what we're looking for is we want to know for each size that's possible, each subsequent size, we want to know firstly if it's even possible, if we even got there. That's the first thing. And the other thing we want to know is like if such a subsequence exists, and then for all those subsequences that are of that particular size, we want the subsequence at each index. We want to know what we want the smallest last value for that subsequence. So for instance, like for 1, right? So let's say for 1, you have 10 at this point. But then you have 9 is smaller at this point. 2 is smaller. 2 is still the smallest subsequence of size 1. 2 is still the smallest subsequence of size 1. In fact, 2 is the smallest subsequence of size 1 all the way across, right? That's what we're trying to figure out. We're trying to figure out for a subsequence that uses all the elements up to that point, that has access to all those elements up to that point. What's the subsequence of a given size? We want to know which subsequent we want to know the ending value, the last value of that subsequence. What the smallest of all those subsequences, what the smallest of all those last values. And the reason for that is that when you progress and you look at more elements towards the right, because that's the smallest element, that gives you the greatest possibility possible, the most possibility you can get to make sure that if there's another subsequence to consider, that requires you to append it to the subsequence you're looking at. Like let's say subsequence of 3, if there's a subsequence of 4, you can guarantee that you'll capture that subsequence of 4 if it exists, because you already have the smallest possible subsequence value for subsequence of 3 at that point. Hopefully that makes some sense. But that's basically the idea. So you're trying to capture this information, basically keeping track of all the possible sizes that at a particular index of all the possible subsequences. We want to know for each of those possible subsequences the smallest ending value of all of those subsequences. That's what we want to keep track of. And as it turns out, you can actually update that as you go. And what happens, so obviously for 0, we're going to do negative infinity. It's going to be like negative inf, right? Can we make this smaller? We'll do like, we'll do 48, but we'll do like 18. 24. 38. 36. All right, that's good enough. So there are no possible values for a subsequence. Excuse me. For a subsequence of size 0, there is no ending value. There is no rightmost value of that subsequence, right? So we just put negative infinity for everything, right? It's always going to be the same thing. Just basically doesn't exist. But there's a reason why we're using negative infinity. I'll explain. There's part of the algorithm is important. Now, what you're going to do, and obviously, so index 0, oops. Now something important here is these are going to be initialized at infinity, which is kind of interesting that we would do it this way, but I'll explain why in a moment. So basically you initialize your array to your matrix, the initial the initial values for size 0 is a negative infinity all the way across, and the initial value for size 2 and so on, 2 to 7 is infinity. You actually can do this a little bit differently. You don't actually need to use you don't necessarily need to, I'll explain, like, we won't actually need to use negative infinity or positive infinity, because there's tricky things that happen when you use values like this, because they restricted the range to be negative 10 to the fourth and 10 to the fourth, but in theory, if you were actually using the smallest possible value for integer that could be stored in integer, or the largest possible value that could be stored in integer, these negative infinity, positive infinity values would be kind of awkward to work with. There's like a lot of different workarounds and stuff, but you actually want an algorithm that doesn't really require this negative infinity, positive infinity, if you can. Obviously, in this case, they restrained the bounds in such a way where we could use it. You do it this way, but I'll explain later. We won't actually need to use these, but for now, let me say that for now, this is sort of how you initialize the array. So it starts off basically all of these values are negative infinity, all of these values are infinity in the beginning, and then the first value, obviously, you set 10. So basically, 10 is greater than negative infinity, but less than this infinity. So, or rather, really, it would actually be initialized with infinity here as well. 10 is greater than this negative infinity, but less than infinity. So it would be set here. And then 9 is, and so all of these would be the same, though. Now, hold on, there's, now 9, now if we look at 9 is greater than negative infinity, and it's less than 10. So we can update our 10 to 9. And you would stop there, actually. You wouldn't update a sequence of size 2, because 9's not greater than oh, I can keep that up there. I didn't think to do that. 9 is not greater than 10. So our largest increasing sequence at 2 doesn't even exist. We don't even have a sequence of 2 yet. Okay, now we say 2. It's greater than infinity. It's less than 9. We can update 9 with 2. And same thing, we stop right there. We don't update anything else. We still don't have a sequence that increases beyond. We still don't have a sequence that increases beyond up from. We don't have an increasing sequence of size 2 yet. We only have 10, 9, and 2. Right now we see 5, and we say 5 is greater than negative infinity, but it's also greater than 2. So we're actually going to put it, and it's less than infinity. Right? Infinity would be is here previously. It's greater than negative infinity. It's greater than 2, but it's less than infinity here. So we put 5 here. So now we have a subsequence that's I want 48. No. Huh. Anyway, so now we have a subsequence, but now the rest of these are infinity. I'm actually not going to write the rest of this infinity. I'll just put a line down there. So now we go to 3, and we say, okay, 3 is greater than negative infinity. It's greater than 2. It's less than 5. So we can put a 3 here, and then infinity the way down. And then you say, okay, 7 is greater than negative infinity. It's greater than 2. It's greater than 3. But it's less than infinity here. So again, put this on the way down. 6 is 101. greater than negative infinity, greater than 2, greater than 3, greater than 7, less than infinity, and then now finally you have 18, you have 2, 3, 7, but this 18 is less than 101. And then the rest of this is infinity. And what you notice is if you walk backwards from the size of the array, or the back of the array, from in here, you walk all the way back towards the beginning, and you'll see this size 18, 4, the result is 4, and the sequence is 2, 3, 7, 18. So that's the largest increasing subsequence, 2, 3, 7, 18. And the way that this works, the way that you would explain it is, to prove it, is that you basically are keeping information that allows you to know the invariant at each step is, for every possible subsequence that you've seen up to this point, you know what its size is, and you know the last of all the possible subsequences. You can break it down into sizes and keep the maximum size into sizes. We'll just say into sizes, and for each possible size, you know the smallest ending value for that subsequence. And because of that, if after considering this next number, if there's another subsequence to consider that has a better, or for any of the subsequences of these groups of subsequences, right, that are split by the sizes, you may have another subsequence created by considering this next value, and you want to adjust such that you still have that information, that you still know every for all the possible subsequences, including that value, you know the ones that exist, this different sizes, the smallest ending value possible for those sizes. And then as described, this is how you would keep track of that. You would basically scroll down your list for each size and say, okay, this new number we're considering, if it's larger than the values we're looking at, that means that it has to go down to a further size for the subsequence, right? Because we can add it to any of these subsequences that it's larger than to create the next one. So we would scroll down the list to figure out, okay, well, which subsequence should we add it to then, to consider, what to get a larger. And all of the subsequence that it's larger than, you don't want to update those ones, because you already have a subsequence of that size with a smaller value. So you would skip those ones. So you skip all the ones that are smaller, but the ones that are larger, the first one that's larger is the one you want, because now that subsequence becomes updated with you can get to that same size subsequence with a better number, with a smaller number. So you've improved that spot. Now you don't go beyond that either, because that's the best you could do up to that point. You actually can't append this value to that point, because it's smaller. So you wouldn't get that size, that subsequence is as big as you can get up to that point anyway. So you would update that point with a new value. And if you go all the way off the grid, right, with this in the infinity, basically, that means this number is larger than any other numbers you've seen yet. So you actually can get a new size. You can actually increase the size of your longest subsequence. And you might have realized or noticed that if this works, and this is quadratic time, right? This is O of n squared in the worst case. If you somehow end up filling this entire matrix, what you may have realized is that you actually don't even care about the whole matrix. You really only care about one row at a time, because each row depends on the previous row. And so you don't even need a full matrix. And not only do you not even need a full matrix, you can just use a single row each time, or a single column that you update each time. Not only do you only need a single column, but as I described, you're literally looking for, with this number, you're actually looking for which number is larger. What's the first number that's larger to update? So what that means is that, and you're only updating that spot. You're either going way off the edge to add a new, basically a new row, or somewhere in between you're updating one of these numbers. Or it could be that it's not smaller than anything and you don't update anything, right? Like if you pick, for 10, 9, and 2, and then 5, well actually 5 is greater than 2, but I'm trying to think of an example where you don't update anything. Actually, I think all of these ended up updating something. But you could be in a situation where, like, if you saw, well, yeah, actually it does matter. You kind of always update something, I think. Or it seems like you tend to update something. But basically, yeah, if everything is large, if there's nothing, if you go off the edge, you actually just add another row. If you go off the bottom, if you are smaller, whatever you're smaller than, or the first thing that's greater gets updated by the value, and that's really it. That's the whole algorithm. Now the reason why I say that, you may have noticed that you're looking for, and these numbers are sorted. You're looking for the first number that's larger. That can be done with a binary search. That's just a logarithmic search over a sorted list. That's a very easy thing to search. So that gives you your n log n algorithm. Is that you actually, for each number, you've got this other vector that you're maintaining, and you're going to do a binary search for where this number should fit in that array. And if it goes off the edge, you just add another layer to that array, another row, really just another element, or another section. And with that element in it, you push that on there, push it back. And if you find the spot, you update the spot, and if you don't, then it goes off the edge. Then you append it to the end. And that's it. That's the whole thing. And then at the end of that, you return the size of the array. Done. It's like super succinct, super interesting, pretty simple. Like, I really like this problem. This is a pretty interesting problem. I realize it took me a while to explain it, but that's what we're going to go for. And this, obviously, would work. The one that I had before, that recursive memoized function. However, it's very slow. I think it's exponential time, potentially. Yeah, and obviously our time limit exceeded, so it's too expensive. Whatever it is, it's too expensive. I don't actually know what the runtime of that is. It's kind of hard for me to figure it out on the spot, but this runtime shouldn't be too bad. So we're gonna have sequence, we'll call it. We're gonna say for int I equals 0. You actually don't even need to do it that way. You could just literally do auto x in the numbers. We'll say standard upper bound of, now I just want to double check CPP-ref. Upper bound will find the first one that's greater than or equal to, right? I want greater than, not just greater than or equal to. The first thing that's greater than, which this is a routine that, oh, no. Keep clicking that. It's going to keep giving me those, which is not what I want. We want upper bound. Not less than, greater than or equal to. Yeah, we want upper bound. And we also want, it returns an iterator, which is really important because that's actually more so what we're after. So we're going to do sequence.begin, sequence.end, the first auto it, right? And we say if it equals sequence.end, then we're going to set, we're going to sequence.pushback x, and we're looking for x, by the way. So first position that's greater than x. If we don't find it, we push back x. Otherwise, we're going to say it is going to be updated to x. And that's really it. Something like this. Something like this. Also, I may need to, oh, there you go. I may need to update something here. So hopefully that explanation made sense. Let me just refresh this page, just in case. Let's give it a moment. Okay. Yeah. Super succinct solution once you realize it. I don't know what other test cases I had for this question. I don't think I had some other ones here. But really, yeah, really neat. I really like this problem. And then we'll add the last one in there too. All right, how do we do? How do we do? Oh no! Come on, really? No! What? Uh-oh. Oh, I thought it was so smart. 7 and 13. Really? 1 and 8. Uh-oh. Uh-oh. What happened? Oh no. And here I was thinking I was a genius. Oh, these are... Oh, okay. I guess you can have duplicates. Alright. Alright, never mind. In that case, it's got to be lower bound, I think. Greater than or equal to, then, is what you update it with. Yeah, alright, whatever. Good thing I checked the cases. Alright, do we go for it? Let's say I just want to test one more thing, like just simple. Alright. Yeah. Alright, let's go for it. Boom. Got him. Yeah, so that, nice, that feels good. That's a good feeling. That's super simple, super succinct. But that's, you know, that's the n log n time complexity. Make you feel like a genius, man. Make you feel like a genius. I do feel like a bit of a schmagoo, though, not knowing the, like getting it wrong, I guess, the first time. Oh yeah, I was one of the ones who got it wrong. I'm looking at this like, oh, submissions and accepted, and I'm like, oh, I got it right. No, I initially got it wrong. Whatever. Whatever, man. Whatever, man. But I do feel smart having figured that out. Amazing. So yeah, GG. Hopefully that explanation was, yeah, it was like 30 minutes it took to explain all that, but obviously it takes 2 minutes to code it once you get it. Pretty straightforward idea. Yeah, all right. I guess that's it. I don't know. That seemed like such a big deal to me, man. Like it still seems like kind of a big deal. I'm like really feel good about realizing that. It's kind of a eureka moment, but pretty hard to do that. Like other kind of brute force-ish type of approaches. Yeah. Anyway, all right. That'll be it for this problem. Thank you for watching. I appreciate it. Talk to you soon. And yeah, man, that's super clever. That's a really neat solution. Really interesting problem. Yeah. Okay. All right. Let's go. Let's move on.